So thank you very much to Yule and to Aviral for inviting me to give this keynote. It's really a pleasure to be here. So indeed today I'm going to talk about fuzzing, and I'm going to offer some reflections, and I'm going to discuss some of the open challenges as I see them. Of course, this talk is going to be shaped by my own experience working in fuzzing. And I've actually done work in fuzzing for many years now. All right, you did the slides did switch. So this is actually the first paper that I wrote on fuzzing. It's on whitebox fuzzing, also known as symbolic execution or dynamic symbolic execution. And yeah, time flies. So it's almost 20 years since I've written co-authored this paper, and yeah, it also has a cool title, I think. So since then, I've continued to do work on fuzzing, on all forms of fuzzing. So in terms of, I've continued to do a lot of work on symbolic execution or whitebox fuzzing. And if you look at this, the title of this recent paper, you can actually see where, what my dream is still is to run symbolic execution forever. I've also done a lot of work on greybox fuzzing recently, and that's, for instance, one of the projects that we've worked on was on high throughput fuzzing for network applications. And most recently, I've started to look at blackbox fuzzing, particularly grammar-based fuzzing, and particularly in the context of compiler testing. Although this paper that I showed here, which I will discuss a bit later on, is not on compiler fuzzing. So, the three colors of fuzzing are white, gray, and black. But I think actually fuzzing is much more exciting than that. So, I added a splash of colors here to the right. So I think everyone pretty much familiar with the different forms of fuzzing. So I see most people nodding, but just in case there are a few who are not, I'm just going to do a very, very quick introduction. So blackbox fuzzing, the reason it's called blackbox is that you're treating the system as a black box. You're just observing essentially how it behaves based on these interactions with it. And perhaps the most common form of blackbox fuzzing is grammar-based fuzzing. So the idea here is that you have a grammar like this one, simplified JSON grammar shown here, and you are going to then work it randomly, and you're going to essentially expand all the non-terminals until you manage to generate an input like this one. And of course, you can generate many inputs to test your program with. And blackbox fuzzing has many success stories. I'm going to mention a couple of them. So I mentioned already compiler fuzzing. So a project like CSmith and EMI are based on grammar-based fuzzing. In the case of EMI with some other ingredients as well. But very successful. Found hundreds of bugs in mature compilers. Also very successful in the context of database testing, for instance. The SQL Answer system is one such example. Greybox fuzzing now is perhaps the most popular form of fuzzing these days, widely used in industry. The idea is that you start with a set of inputs. You're going to select an input. You're going to do lots and lots of mutations, and then you're going to measure whether these new inputs get more coverage to the program, and if so, you're going to add them to the input queue, and you're going to iterate until your time budget is over. And that's a form of greybox fuzzing called the coverage-directed mutation-based fuzzing, which is, I would say, the most popular form of fuzzing these days. And then, in terms of success stories, there's a couple of examples. AFL really has revolutionized greybox fuzzing and has a long list of trophies. And you may have heard about Google's OSS Fuzz, which is actually a fuzzing platform, where they actually run many of these greybox fuzzers and looking for bugs in open source software. Actually, they managed to find today like an impressive number of bugs using these techniques, over 36,000 in over 1,000 open source programs. So now, whitebox fuzzing, also known as I said symbolic execution or dynamic symbolic execution, the idea here is to systematically explore paths through the program using a constraint solver underneath. So what you're going to do is that instead of running, let's say that I have this piece of code here, instead of running it on a concrete input like k equals 10, I'm going to run it on a symbolic input, all right, which initially is allowed to take any value. And when I reach a branch that depends on the symbolic input, either directly or indirectly, I'm going to check the feasibility of each side of the branch, and if both are feasible, I'm going to fork execution and follow each path separately. So for instance, here on the true path, I'm going to have the constraint that the branch condition is true, so k is it mean, and then I'm going to continue execution in the same way. I mean, here I just return -1 and I'm done. For instance, on the false path, where I have the constraint that the branch condition is false, so k is not in mean, I'm going to continue execution, and I'm reaching this other branch, k is less than 0 again. I'm going to check the feasibility of each side of the branch. This time I do have a constraint on this path, which is k is not in mean, but of course both sides are still feasible, so I'm going to follow both. I'm going to end to have the constraint that the branch condition is true on the true path, and I'm going to return -k, and the constraint that the branch condition is false on the false path, and I'm here, I'm just returning k. So now, at the end of each of these path traversals, I can take the set of constraints that I collected. For instance, here I have k is not in mean and k is less than 0. I can ask the constraint solver for a value. Let's say it gives me k equals -5, and now I have an input which is guaranteed to follow the same control flow path that was followed during symbolic execution. So in terms of success stories, again, there are many. For instance, Microsoft Sage is credited to having found 1/3 of file fuzzing bugs during the development of Windows 7 using this technique. And Eli mentioned CLI, which is an open source tool widely used in both research and academia. And because we're maintaining CLI and maintaining and developing it in my research group, you can see I also have a nice sticker here on my laptop. I'm going to take like a very quick publicity break if you want to tell you a bit about CLI. So it is a system for symbolic execution or whitebox fuzzing. It works at the level of LLVM bitcode. So as long, we've used it primarily for C, but it also has some support for C++, for Rust. And in fact, as long as you can compile your code to LLVM bitcode, is going to work. I'm quite excited about the impact that CLI has had both in academia and industry. So in terms of academic impact, this work led to a couple of Test of Time awards. Lots of citations, but I think what's very exciting to me here is not the number of citations, but the fact that they actually come from so many diverse fields, like security and programming languages, which actually shows in and CLI is useful to the community. And we've also seen growing impact in industry. So for instance, here I mentioned some of the companies that have published papers or given talks or wrote blog posts, about experimenting and using CLI for their own systems. And we have an active community, but we're always looking, for more interested people. So definitely, one thing that I hope that you'll take away from this talk, maybe check out CLI to see if it's useful for your own research. We also have an ongoing workshop series on CLI. So we just had the 4th workshop in April in Lisbon, co-located with ICSI. And the first 4 editions, have gathered together over 400 participants to date. So it's quite an active workshop series. So definitely consider a future edition if you're interested in this area. All right. So now I'm coming back to my talk on fuzzing. But before actually I talk more about fuzzing, let me actually talk a little bit about manual testing, because I think it's important to understand how developers actually test their programs in practice these days before seeing if we can help them with fuzzing. So 10 years ago, 2014, we conducted this empirical study where we analyzed 6 popular open source systems. We looked at 250 patches in each of these systems, and we tried to understand how developers are testing, their code as it evolves. And, the one-line conclusion was that unfortunately, lots of code was being added, or modified without being tested, sometimes not at all. So now, 2024, I was actually quite interested to see if things have changed, whether, we are doing better. We've seen, many changes, like CI frameworks, like fuzzing, coming into play. So I had a very good master's student who tried to look and, to replicate and to extend this study to, the latest decade. And we actually looked at the same 6 systems plus 3 more. So you should recognize many of these systems. They are widely used, things like APR, binutils, curl, git, LCTES24, memcached, Redis, Vim, and 0MQ. So these are the time spans that we considered in this study. The hashed areas to the left are the ones that we considered 10 years ago. So this is basically the rest is since then. And we have 3 more systems where they don't have any hashed areas. So in total, we looked at between 3 and 14 years of development time per project for a combined 78 years of development time. So quite a lot of data. So we have actually many interesting conclusions. I'm just going to give you a couple which are most relevant for this talk. So first of all, I guess you're not going to be surprised to see that systems keep growing, okay? And here you can see, essentially, for those periods considered, like the evolution of the executable lines of code for these different systems. And you see that they add a lot of code, right? Both in absolute values and in percentages. I think that's definitely a problem here, that's a lot of code bloat here. I mean, if you look at these systems, their core functionality in some ways has remained unchanged. Of course, many things have to change, but perhaps not at this rate. But, that's the topic for another talk, and, although I'm happy to chat to you during a break about this subject. But code does grow tremendously. Now, how do the test suites keep up, all right? So we have a mixed, picture here. So a bit of big news, good news is that the coverage achieved by the developers' test suites does increase over time, right? Although we do have one application, Redis, here, where it does decrease. So these are basically line coverage and branch coverage over time. However, despite the fact that they do increase over time, which is good, I think we have to consider 2 things. One of them is that line and branch coverage are quite a low bar, of course, for testing. But the other thing is that some of these applications start from very low values to begin with. I mean, look at binutils, look at LCTES, right? Look at even Vim, right, which starts from just above 40-something% for branch coverage. Although Vim, as you can see, they've done a lot of progress in this period. So that's overall coverage, right, of the test suite. I'm actually more interested in patch coverage, all right? So how well patches are tested. And the reason I'm interested in that is that if you look, for instance, at the security vulnerabilities that made the news, things like Heartbleed, right? I mean, these security vulnerabilities have been introduced by software patches, right? So I think that that's really important to, and challenging to actually test the software as it evolves, right? And here we actually looked at how well patches are tested. So what we do here, we measure patch coverage. So what's patch coverage? Let's say that a patch modifies adds or modifies 10 lines of code. all right? Now I look at the test suite, how many of these lines are exercised, right? If it's 6, it's 60% patch coverage. If it's 2, it's 20% patch coverage. So here for every of these systems, I'm grouping these patches by patch coverage. So for instance, the ones in dark green here are 100% covered, given this metric, while here in the dark red, they are 0% covered. And then we have like things in between. So I think we have a big problem here, right? A lot of code continues to be added or modified without being tested. Sometimes not at all, all right? I mean, if you look at this dark red. And in fact, things are even a bit worse because here I treat every patch equally. But as you can imagine, a patch which has like, 2 lines of code, it's much more likely to get high coverage than one that has like 200 lines of code, right? And the other thing, again, this is a very low bar. A lot of this coverage, in fact, it's incidental, right? They're not really testing the patch, the behavior introduced by the patch. They're just touching the lines of the patch. So, can fuzzing help? So I think the answer is yes, but. All right, so I'm going to tell you about some of the challenges. So I'm going to start with the fact that fuzzing tends to generate either too many invalid inputs or too many valid inputs, okay? So I think with too many invalid inputs, it's more easier to understand that this is a problem, right? So for instance, with greybox fuzzing, you're generating a lot of random inputs. And even with whitebox fuzzing, where you're very systematic, if your search space is dominated by invalid inputs, well, that's what you're going to systematically explore. So often what happens is that, with these fuzzing techniques, particularly greybox and whitebox fuzzing, is that you're going to generate lots of, ugly-looking inputs that actually are invalids, okay? And they don't make it to the core functionality of the system. And a lot of the research, in fact, in greybox and whitebox fuzzing try to solve this problem. How do we generate, meaningful inputs? And there is a lot of research in terms of mutation strategies, exploration strategies, better coverage metrics, eliminating redundant explorations. So I won't have time to go into too much detail here, although I will touch upon one of the techniques, exploration techniques, later on. So now, interesting enough, for whitebox fuzzing, you actually have the opposite problem, if you think about it. For instance, if we look at grammar-based fuzzing, right, you have a grammar. I'm going to traverse it randomly. By definition, I'm just going to get valid inputs, all right? And what's the problem with this? Well, let's actually first look at consider, the inputs accepted by the SUT, right? The SUT stands for System Under Test. The inputs generated by the grammar. So in theory, these are the same, right? Now, in practice, things are a bit more subtle, okay? They are actually, these two actually differ in practice, okay? So what are the implications of this? So the biggest implication is that we're not going to explore this top left corner, right, which are inputs accepted by the SUT but not generated by the grammar. And why is this a problem? Well, this is a problem because you are missing the kind of potentially critical bugs where the SUT is incorrectly accepting an input that it should reject. And of course, if this input is, for instance, malicious, right, in a security context, that's a big problem. Another thing that this, this left, upper left inputs can reveal are bugs in grammars, right? Because there may be actually, there is an issue with the grammar because it's unable to generate some valid inputs, okay? Now, we also have this bottom right corner where essentially these are inputs generated by the grammar which are not accepted by the SUT. These are less interesting in practice. I won't go into detail, but perhaps the more important thing is that these are already generated by grammar-based testing because they can be generated by the grammar. So here's, and then you also have like these slightly invalid inputs, right? Which are actually you really like to explore because many of the bugs are there. So that's actually quite an interesting point, and it's not very easy to formalize this. So if you generate completely random input, so as I said, I'm working on compiler fuzzing. So if I manage to generate like a random string that crashes, you know, GCC and Clang, the chances of that input being fixed, of that bug being fixed by developer through this bug report are very close to zero. And that's because compiler developers have so many bugs to deal with, and they're going to deprioritize essentially like just some unrealistic input, you know, that pretends to be a program that causes an issue in their compiler. I mean, of course, it should be fixed if they have time, but that's often, you know, time is a big but. Now, if you give it like a program that it looks almost correct, then yes, they are going to pay attention, and I can tell you firsthand, you know, about these things because, you know, they think that this is realistic, right? So that's what I mean by kind of like, you know, slightly invalid inputs. So here's our recent idea that we've experimented with that tries to generate this kind of interesting inputs with grammar-based fuzzing. And this is grammar mutation, right? So I mean here, like, we actually mutate the grammar. So I take my grammar G and some SUT that I want to test, and then I mutate this grammar G to generate a grammar G prime. And then I'm going to fuzz, you know, the SUT using G prime instead of G prime, and now I can actually look for these non-G inputs which are generated by G prime that are accepted by the SUT. And of course, I can try many, many different mutant grammars. To make things more concrete, here are the kind of mutation that we've experimented with, but of course you can try many other things. So just as one example, you know, if we have a repetition 1 too many, we change it into 0 or more, right? So 1 or more to 0 or more. Or we maybe add an extra choice as part of a rule, right? So perhaps the key thing though here is that these mutations are monotonic. And actually, initially we thought that, you know, they shouldn't be monotonic, but the reason for making them monotonic, so what I mean by this is the language of G prime is a strict superset of G. That's actually because you want to be able to generate any input that G was able to generate and then do these localized mutations, right, to any input. So this seems actually quite useful for generating the kind of inputs that I discussed. So we implemented this into a system that we call Gmutator. We tried it for grammars, for JSON, for Lua, for URL, and for XML. We took, and for various SUTs, you know, for these languages. And actually, we did find 10 bugs that were confirmed, 6 already fixed, which are out of reach of regular grammar-based fuzzing. And interesting enough, we started Antler, if you know, it's like has a repository of grammars for many different formats. And that's what we use here. And actually, we did find also 3 bugs in these grammars, which were all fixed to date. All right. So I'm going to move to a different part of my talk where I'm not going to focus not on overall testing, like I've just discussed, overall testing of a program. I'm going to look specifically at testing changes, okay? That, as I discussed, a lot of the problems are introduced by changes. So, can fuzzing enable better testing of software changes? So again, we have a yes, but. So one big issue is that fuzzing is often not agile enough. So if you look at most of the fuzzing techniques being developed out there are for whole program testing, all right? And in fact, most of the benchmark suites that are in use measure global metrics. How many bugs did you find in this program? How much coverage have you achieved in this application? As opposed to essentially how well did you test this patch and whether you found bugs in that patch, in that code change. Now, there has been good progress recently on these techniques, but I think the results are still poor compared to whole program testing. And I say here, one reason is that having done both, testing doing like whole program fuzzing, it is easier than doing patch testing. This being said, there are actually good opportunities for for testing changes, patches. And of course, one thing that you can do is targeted exploration, right? So these are two pieces of work that have looked, so, you know, that's a catch which we developed, which tries with symbolic execution to target, you know, with various heuristics, the patch code, and that's the AFL Go system that was developed with the same goal, but using greybox fuzzing. And the other direction that you can exploit is to reuse previous analysis results, right? And this is what this running symbolic execution forever had to do. So, you know, if you analyzed your system for version 1, then you actually can reuse the results to do a much better, much quicker exploration of in version 2, right? And we're also looking to try to do something similar like to this for greybox fuzzing. So let me actually show you one technique for targeted exploration that we have developed. So we're trying to prune the search space unrelated to the patch. So suppose that you have like this call graph, and our patch is here, right, at the bottom. So now, you agree with me that in many cases, right, the code where the patch is has nothing to, you know, there are many, you know, it's unrelated to a lot of other code, right, but of course not all. So let's say that, you know, I knew that in this call graph, foo, zab, and buzz have nothing to do with the patch. Then, well, I could just eliminate them, and now I can really focus my fuzzing on the piece of, you know, the part of the code that really is relevant to the patch. Now, the problem is that if you want to determine precisely ahead of time if a part of code is unrelated to another, this is very hard, okay? And in fact, what we observe that often most computation in a code fragment is unrelated, but not all, okay? So our idea, which we call chopped symbolic execution, is as follows. Instead of trying to make this determination statically or, you know, ahead of time, which is very hard, we're just going to have a guess, right? Maybe this is by some lightweight analysis. Maybe this is even manual in the, you know, when you do, you know, in a certain context when you have developer involvement. And then we're going to speculatively skip these code fragments, right? Eliminate them essentially from the program. And only if we discover later on that there are side effects, you know, what the code has done is actually turned out to be important for my execution, I'm going to come back and try to execute the relevant paths through the skipped code. All right, so let me show you how chopped symbolic execution works. So you have, let's take this example where I have my input A, which is symbolic, and I also have this global variable Y, which I initialize to 0. And then this is my main program. I start by calling F. Then I have, like, you know, these if statements that reach these targets, target 1 and target 2, which are essentially my patch, if you want. And this is the function F. So here it's really trivial. It only has like one if statement, but in reality, it could be like a huge piece of code, right? So now let's imagine that this huge piece of code, which here is just like one branch, it's actually not needed. So if that's the case, maybe, yeah, let's skip it. But before we can skip it, what we need to do is a couple of things. First, we need to actually compute the ref set of main. I want to know what memory location may be read in this code. Okay, so here is, for instance, A and Y. And then I want to know what memory location may be written by the code that I want to skip. So the mode set of F, which is Y. All right, so this can be done statically. You do need points to analysis. You know, we're very happy to use Euler's SVF system for that. And we have a few other tricks that are, you know, which we can exploit in the context of symbolic execution. But I'm not going to focus on that. Let's say that you made this determination. So now what we're really interested in is basically the intersection of the two. So we're interested in these dependent loads. We're interested in any memory locations that may be read in the main part of the code, which may have been written in the skipped code, right? That's what can get me into trouble if I skip the code. So with this in place, I can start symbolic execution, all right, as usual. So my input is A, initially is anything. When I reach F, I just skip that code, okay, which could be, again, like hundreds and hundreds of lines of code, could actually have a huge number of paths. Often it's exponential in the number of branches in that code. So I skip it, but I do take a snapshot at that point so that I can resume execution if I need it later on. I remember the program counter, the stack, the path constraints, and so on. Then I continue execution. So I reach this if statement, if a greater than 0, you know, both sides are feasible. So symbolic execution is going to explore both. Let's see what happens on the false path. Well, on the false path, I had the constraint that A is less than or equal to 0, right? The branch condition is false. And I continue execution. And now, I'm already very happy because I reached target 2 without having to execute a single line of code in F. I could have had like a huge number of paths through F where I'd have wasted a lot of time. So now I can just don't need to do that. Now, things are not always as rosy. So, you know, on the event side here, I'm actually going to reach this dependent load. So now I'm asking, like, you know, is Y non-zero? Well, I don't know because Y could have been written by F. So now I actually do need to go back to F and see what has happened. But actually do remember that I'm interested in what has happened to Y when I reach this point where I already know that A is greater than 0. So that's really nice because now I can only execute F symbolically under the assumption that A is greater than 0. And under this assumption, you know, only this path is feasible. So I communicate the fact that Y was set to 1, so now I can actually reach target 1. So we've had a preliminary, you know, evaluation for this, and actually we didn't do it for patches, we did it for reproducing security vulnerabilities, but it's a very similar problem. You have some target parts of the code where you think the problem is, and now you try to generate inputs that reproduce those issues. And the bottom line here is that when we compared CLI with this chop symbolic execution implementation chopper, you can see that for 3 of these CVEs, for instance, like, you know, CLI either timed out or ran out of memory, while skipping so much code, you know, we were able to reproduce these vulnerabilities in a very short time. All right. So now I'm going to go to the last part of my talk where I'm going to say that fuzzing also often like is not thorough enough. So what do I mean by this? So by this I refer to actually this Oracle problem, right, in software engineering, where, or software testing in particular, where you try to determine if an execution is correct, right? So I can generate lots and lots of inputs, but how do I know, basically I run them, how do I know if I found a bug? So now, of course, the easiest thing is to find generic bugs. Null pointer dereferences, buffer overflows, use after free errors. There are lots of them for you know, C and C++ code in particular. And in fact, if you actually look at, I mentioned OSS Fuzz that found over 36,000 bugs, right, and you know, over 10,000 security vulnerabilities. Well, those security vulnerabilities all involve these problems, right? Now, if we're moving away from C and C++, or if basically this fuzzing techniques manages to get rid of all these vulnerabilities, can we still use fuzzing to do more, right, to check other kind of properties? And that's hard, but I think it can be done. I also mentioned here that, of course, we also always have the issue of fully verifying software. But I think, as you know, this is extremely expensive. Yes, there are, like, you know, systems that have done it, things like CompCert, things like SEL4. But we're talking about years and years of PhD level expertise and, you know, specifications typically much bigger than the code itself, right, that went into those systems. And they're still, like, you know, not competitive in many aspects with, you know, the non-verified counterparts. So is there something in the middle? You know, I'm actually very interested in my research in this question. And I'm going to show you one thing that we've done in this space recently. By the way, in the middle, we have this partial or relative correctness. So we give up on checking full correctness, right? But we also want to do more than just generic errors, okay? So I'm going to look at one thing that we've looked recently are patch specifications, right? Also, this relates to what I've just discussed, the fact that we do want to test patches comprehensively. So what's a patch specification? Well, a patch specification is simply a property that encodes cross-patch properties. So, the version, so let's say like, in the version after the patch, I have this variable out. And now I say, look, I know that the patch should have, the way it has computed out, now it should be the value that it had at the program point in the previous version, so this outprev, plus 1. Okay? So that's an example of a patch specification. So now, sure, you can write these patch specifications, and in some cases, actually, they are easier to write than a regular specification, right? These absolute specifications, if you want. But then, how do we use them? Okay, we need to be able to refer to the, to outprev in some ways. So here is where product program come to play. Anybody knows about product programs? All right, so product programs are something that comes from the security community, right? So at a high level, they're just a way to merge two programs into one, typically two program versions of the same program with itself. And the reason they are used in security is to reason about these hyper properties, right? Things like non-interference, where you actually need to analyze not a single execution at a time. You need to analyze pairs of executions to be able to determine if there are any security leaks, for instance. So in that context, you basically just do the product of a program P with itself, all right? So here we're interested in terms of patch specification and patch testing, in whether these product programs can work for multiple versions of the program, whether they can be constructed automatically for large programs, and whether they can facilitate the writing of patch specifications. So let me make things concrete. Again, I'm going to use this very simple example. So if I have in the previous version, it's something like x equals y minus 1 and z equals x over 4, and in the current version, I change x over 4 with x shift 2, right? Then the product program is going to look something like this. I'm going to rename all the variables in one version. Let's say in the previous version, I'm going to add the suffix underscore prev, and I'm going to basically interleave these statements, all right, in the two programs. So very easy. So once I've done this, now this patch specification like z equals z prev does make sense. And in fact, I can use symbolic execution, I can use greybox fuzzing, I can use any techniques that I out of the box on this product program. Now, of course, the construction of a product program is more complicated when you have like constructs like loops and function calls, but it can be done, and our ongoing work is quite positive in terms of the ability to do this for real programs. So let me just end by telling you about some preliminary experience that we have with these patch specifications. So we wrote patch specifications for several patches from this core bench suite of regression errors. And what we did, we constructed test driver around the functions involving patches, and then we use AFL++ and CLI to look for violations of these patch specifications. So let me show you a patch in LS, okay, for which we wrote patch specifications. So the patch was in this make link name function, okay, that takes a name to a file, and then the name of a link, of say a symbolic link that you want to create, and then it returns the full path to the symbolic, to the link, right? So if you say a/b/f.text and g.text, it returns a/b/g.text. And the patch that we looked at, the commit that we looked at, had the following message. It said, do not hardcode / use this absolute file name and dir len. Instead, use stp copy, stpn copy in place of strn copy and str copy. This was supposed to be a refactoring patch. Okay, you can also tell it from the commit message. And here's the actual patch. You don't need to understand it, but you can see that it's doing what the commit message was saying. It's using, instead of this equality against /, it's using this macro, is absolute file name. Instead of doing this third chart to look for the /, it's using this function dir len, and then it's replacing essentially stp n copy and str copy with this stp copy, stpn copy, okay, which is supposed to do the same thing. We wrote 3 different patch specifications, so these simple asserts for this patch. I'm going to focus on one of them, the most obvious one, where we say that because this is a refactoring, we want in the end, the outputs to be the same, right? So if I compare P, which is the pointer to the string that this function returns, and it should be the same as pprev under stir compare. So once we wrote this patch spec and we ran AFL++ and CLI, they both found a violation quite quickly. So this is actually one input that was generating /a for name and the nickname X, so quite a simple input, but it does show a difference between the two. And this was a bug that made it into a release version of LS. What happened is that a user then reported this bug, and then the developers fixed it. But the bottom line here is that, of course, with these very simple patch specifications, the developers would have found the bug before making it into a release of LS. So here is actually the patch that the developer pushed in response to this. Again, don't need really to understand it, but it's dealing with some corner cases there. Interesting. So now what we did was to incorporate this patch and repeat the process. Okay? So see, okay, can we find more patch violations? And we didn't expect to find any more, except that we did. And here is basically another set of inputs that were generated by FL++ and CLI. So this time this involved these double slashes. Okay, so we looked at this difference. So the two versions did different things. We looked at so we looked at this bug, and we believe it's not really a bug, and that's because if you look at the POSIX specifications, it tells you that double slashes are the same, can be used for single slashes. But I think you agree with me that developers, if this meant to be a refactoring, they should have documented this test case. Ideally, they would have added such a test input to the regression test suite, to make sure, and to communicate the message that this was an intended patch, maybe, an intended change in behavior. But nevertheless, so the patch was still violated by this input. So the final thing that we did was to change stir compare with this path equality function, which essentially normalizes multiple slashes into a single one. And with this, we couldn't find any more patch spec violations. All right, so I'm quite excited about that. I think that's quite a promising way for this kind of partial forms of functional correctness. So I've reached the end of my talk. So the only thing, because, as Yule was saying, these days you even have a new topic of LLMs to the to the conference. I thought that, in 2024 it's hard to have a talk without any reference to Gen AI. So I'm going to end on that note. What's the impact of Gen AI on fuzzing, right, and on software engineering in more broadly? So I see 2 possible futures. One future is one in which Gen AI is going to do everything for us, all right? So it's going to write perfect code, correct by construction. There's nothing for us to do other than kind of talk to the AI to say what you need. Now, I think that's actually quite an improbable future, except for perhaps some niche, domains here and there. I think the more likely future is what AI-assisted software engineering, right? So here we're going to see this very accelerated shift from writing code to reviewing code, right, that AI has generated for us. And I think in this future, effective fuzzing techniques will actually become even more important than they are today, given the amount of code that will be AI generated. So this brings me to the summary slide. So I hope I convinced you that manual testing is not enough, and unfortunately we're seeing lots and lots of code which is added or modified without being properly tested. I think fuzzing techniques clearly can help, but they're still not enough. They're not agile enough, they're not thorough enough. There are several not enoughs that I haven't managed to cover in this talk, so we're not there yet, but I think they can already be very helpful. And as I said, I think now with Gen AI coming into play, I think effective fuzzing techniques will become more rather than less important. So with this, I'm very happy to take questions.
Thank you very much. Thanks for the wonderful talk. So any questions?
Okay, thanks for a nice talk. Although you said that there are not enough, I would like to ask something that we also face nowadays when we have operating systems that also have patches, also have some unclear version of different patches, and furthermore, most operating systems are not formally verified. So how do you see that such fuzzing logics could be applied, for example, to some specific operating systems that may involve safety issues? Of course, it is too complicated.
No, that's a very good question, and indeed it's one of the challenges that haven't made it to this talk just because of the time constraints. But yes, I think a lot of fuzzing, so the challenge is actually using fuzzing for other application domains. So right now, I mean, I think fuzzing has started with perhaps like, the easy bits. There's a lot, for instance, file fuzzing has been extremely successful, and if you look at tools like AFL, like, like CLI as well, like, they are targeted toward these applications where, it's kind of like user level code where you have like, some files typically as your input, and then you try to fuzz that. I think there are many other kind of applications which are much more complicated than that, right? Operating systems is one example. There are more. Now, one thing that I think is very promising there is to look at automatically generating test drivers, fuzz targets for various components of the operating system. This is something that we're working on. It's quite a difficult problem. It's actually a challenge in general for testing, even the kind of system that I showed you here, because, fuzzing, it's supposed to be, when you think of fuzzing, you say, it's fully automated. The truth is, it's not. I mean, except for like, some very simple, some applications, some very simple I/O, interface, right? No, it's much more complicated than that. If you want to test like a library that takes like data structures, they need to invoke APIs in a certain order, as preconditions, that's very hard. You do need to write essentially like some test drivers. The same for, parts of the operating system. So I think actually I'd like to see the community investing more time in not just on the exploration part of fuzzing, but also in this generation of test drivers. And by the way, because we talked about LLMs already today, I think that's something that they can help, right? To be able to generate such glue code, right? That fuzzers can use. Thanks for the question.
Any more questions?
It's one.
Thank you. Thanks for the excellent talk. It was really interesting. I was just curious. When you were speaking about symbolic execution and how you follow the code flow through the application, how all the different types, have you thought about applying symbolic execution to highly configurable applications that have like preprocessor directives to turn bits of the code on and off at all? Like that's sort of like a meta level, I guess, of symbolic execution before you get to the real code. Because things like operating systems, they are super configurable, as are complex applications. So there might be code paths that exist in one compiled version and not in another.
That's a very interesting application, a very interesting problem. No, the short answer, we haven't done this. Now, I think it's challenging. I mean, I'd be curious to talk to you to see what thoughts you have. I mean, one problem is that, for instance, with a tool like CLI, we operate on LLVM bitcode. So, we first rely on the compiler generating the code. So basically, it's going to be done under certain configurations. Now, of course, you could try. That's something that you can do, right? Because CLI can also be seen as a bit of a virtual machine. So you could compile this code under different configurations. You can have different defines there. You have different versions of the code that you test. You maybe even can do some cross-checking there, right? So you can compare them. But I think it's very hard to do this elegantly and more efficiently where you just don't do this, without repeating the process n times. And of course, n can be very big, right? And there is research on this product lines, right? So there are certain types of highly configurable systems. There has been like research about how to sample these different configurations, so maybe it could be combined with that. But nevertheless, yeah, I think in general it is a tough problem, and it depends a bit on the specifics, and something that I'd be happy to chat about.
Thank you very much.
Thank you for the presentation. I was just curious to ask if the techniques that you showed, if in C, C++ bases there were extra challenges due to things like the preprocessor or the way code is built.
Yeah, there are challenges there as well. In fact, when we started, when I started with symbolic execution, I was actually using SEAL for the compiler infrastructure from Berkeley as to instrument the code, and that in the end is a research project, a very good one, but still it was very challenging to kind of compile the code. So with CLI, we switched to LLVM. So the nice thing is that we benefit from all the LLVM infrastructure. So basically, we start from the point of after LLVM has compiled the code to bitcode. So I would say many of the challenges are solved by LLVM. There are still challenges, of course, when we try to do various forms of analysis. Sometimes even as a research project, for instance, but these are more like engineering issues. The research project is very hard to keep up with kind of the development in LLVM. You also depend on other tools, let's say SVF from ULE, who also tools which are also facing the same kind of issues, and now they need to be compatible. So there are all sorts of issues like that. When we construct these product programs, this actually becomes more of an issue, in terms of kind of dealing with this code, or again, when we want to generate these test drivers, whatever. Another thing is that what we notice is that if you want to do things at the level of source code, as opposed to the level of intermediate level, it becomes much harder. All right. So, for instance, this test driver generation, ideally, I would like to have C code, right, or C++ code, right, that calls into the functionality of the system. But operating at that level is much harder because there are much fewer tools that know how to deal with source code directly. I'm not sure if this answers your question, but let me know if you have any other clarifications you'd like.
Thanks. So, any more questions? So, yeah, let's join me to thank Professor Cristian for his wonderful talk.